2014, two astrophysicists published a graph that should have made the front page of every newspaper on Earth. It didn't. The graph was tucked inside a 60-page review paper in the Annual Review of Astronomy and Astrophysics, the kind of paper that circulates among specialists and never reaches the public. And what it showed was, by any honest measure, the single most important trend line in the history of the universe. The vertical axis measured the rate at which new stars are born, per year, in a given volume of space. The horizontal axis measured time, stretching from the first few 100 million years after the Big Bang to the present day, and the line, after climbing steeply for the first 3.5 billion years, peaked and then fell. It has been falling ever since. The graph is called the Madau plot, after Piero Madau, who along with Dickinson compiled decades of survey data from ultraviolet, infrared and submillimeter telescopes into a single continuous picture. What they found was a curve that rises, crests and declines with the clean inevitability of a hill viewed from a distance. The peak occurred at a cosmological redshift of about 1.9, which translates to roughly 10 billion years ago, when the universe was only a quarter of its current age. At that peak, galaxies were forming stars at 10 to 30 times the rate they do today. The Milky Way currently produces somewhere around 1 to 2 solar masses of new stars per year. 10 billion years ago, galaxies of comparable size were churning out dozens. Some were producing hundreds. That era has a name. Cosmologists call it cosmic noon, the midday of the universe's productive life, and we missed it, not by a little, but by 10 billion years. The Madau plot does not show a fluctuation or a temporary dip. It shows an exponential decline with an e-folding timescale of 3.9 billion years, meaning that every 3.9 billion years, the star formation rate drops to roughly a third of what it was before. Half of all the stellar mass that exists in the universe today was already in place before the universe reached about 6 billion years of age. By the time our sun ignited, 4.5 billion years ago, the cosmic production line was already winding down. The sun itself is a latecomer, born in the long afternoon of a universe whose most fertile years were already behind it. If you had been alive during cosmic noon, if such a thing were possible, if there had been a planet, a sky, a pair of eyes, you would have looked up into a sky dense with star-forming nebulae, blazing across every wavelength from ultraviolet to far infrared, pillars of gas collapsing into new suns, galaxies glowing with the concentrated fury of creation on a scale that no longer exists anywhere in the observable universe. And if you could somehow see through time, from that ancient sky to this one, you would notice that most of those furnaces have gone dark. This is not a projection. It is not a model. In 2015, an international team of astronomers led by Simon Driver released the results of the Galaxy and Mass Assembly Survey, the largest multi-wavelength census of the nearby universe ever conducted. They measured the energy output of more than 200,000 galaxies across 21 wavelengths, from ultraviolet to far infrared, and what they found confirmed what the Madau plot had implied. The energy produced in a representative volume of the universe today is roughly half what it was 2 billion years ago, and the decline is happening across every wavelength band they measured. Not just visible light, not just infrared, everything. The universe is dimming. It has been dimming for 10 billion years, and there is no known mechanism, no theoretical framework, no hypothetical process that could reverse the trend. The fuel is running out. Not in the way that a car runs out of petrol, where you pull over and wait for help. More in the way that every petrol station on the map has already closed, and the ones that haven't closed yet are running on their last reserves. Galaxies form stars from cold molecular hydrogen, and that hydrogen is being consumed faster than it is being replenished. Some galaxies have had their gas supplies cut off entirely, a process astrophysicists call strangulation, because that is, in effect, what it is. The gas that feeds new star formation is no longer flowing in, and the gas that remains is being used up or blown out by the violent feedback from the galaxy's own central black hole. When Simon Driver presented the GAMA results at the International Astronomical Union's General Assembly in Honolulu, he offered a metaphor that was picked up by every science outlet in the world but somehow failed to land with the weight it deserved. He said, "The universe has basically sat down on the sofa, pulled up a blanket and is about to nod off for an eternal doze. It is a warm image, gentle even, and perhaps that is why it didn't alarm anyone. But the data behind it is unambiguous. The universe's most energetic era is over. The lights are going out, across all wavelengths, in every direction, at every distance we can measure. Not suddenly, not dramatically, slowly, quietly, and with absolute finality. And this slow fading, this barely perceptible dimming that has been underway for longer than our solar system has existed, is perhaps the most unsettling kind of ending. Not a catastrophe, not an explosion, just a curve on a graph, sloping gently downward with no flaw in sight. There is something strange about knowing this, something that doesn't sit easily in the mind. The universe is dying, and has been for most of its life, and yet tonight the stars will come out. The Milky Way will arc across the sky, and none of it will look any different than it did last night, or the night before, or 1,000 years ago. The decline is real, but it operates on timescales so vast that no human civilization could ever detect it by looking up. You would need telescopes, you would need surveys spanning decades, you would need to compare the light output of hundreds of thousands of galaxies and track the change across billions of years. And when you did all of that, when you gathered the data and drew the graph and followed the curve, you would find that the universe peaked before our planet existed and has been fading ever since. Maybe that should be frightening. But there is another way to hear it. A quieter way, the way it sounds at 2 in the morning when you are lying in the dark and the facts of the cosmos seem less like threats and more like context. If there are 2 trillion galaxies and all of them are dimming and the whole enterprise of star formation has been winding down for 10 billion years, then the thing that kept you awake tonight, the bill or the argument or the deadline, is not just small. It is small on a scale that makes smallness itself a kind of freedom. The universe does not care about your deadline. The universe does not care about anything. And there is, if you let it, a strange comfort in that. But before we descend further into what that fading means, how far the dimming goes, what the universe looks like when the last star has burned through its fuel, and what remains in the silence afterward, there is something I want to ask you. If you're still listening at this point, if the sound of these numbers and these distances hasn't driven you away but has instead pulled you closer, then I think this channel might be the kind of place you return to. Consider subscribing, not because I need you to, but because what comes next in this story is the kind of thing that changes the way you look at the sky. And if you've ever learned a cosmic fact that made you pause, something that made the universe feel a little too large, or a little too old, or a little too quiet, I'd like to hear about it. Leave it in the comments. I read all of them, because the graph does not stop here. The Madau plot shows the decline from cosmic noon to the present day, 10 billion years of fading. But the present day is not the end of the story. It is not even the middle. What the plot cannot show, because the data only extends to the current epoch, is what comes after. And what comes after is a descent so long, so slow and so absolute that the 10 billion year decline we've already measured is, in the full scope of things, barely the opening sentence. The curve keeps falling, and eventually it reaches zero. In the autumn of 1995, Robert Williams did something that nearly cost him his reputation. Williams was the director of the Space Telescope Science Institute, which meant he controlled a portion of the observing time on the Hubble Space Telescope, the most powerful astronomical instrument ever built and one of the most oversubscribed. Every hour of Hubble time was fought over by hundreds of research teams, each with pressing scientific questions and carefully justified proposals. And Williams decided to spend 100 consecutive hours, 10 full days, pointing the telescope at nothing. Not nothing in the colloquial sense, nothing in the astronomical sense. He chose a patch of sky in the constellation Ursa Major, roughly the size of a tennis ball held at arm's length, that appeared to be completely empty. No bright stars, no known galaxies, no catalogued objects of any kind. Just a tiny square of black. His colleagues thought it was a waste. Some of them said so publicly. The telescope could have been studying supernovae, or mapping the surfaces of nearby planets, or tracking asteroids. Instead, it was staring at a blank spot in the sky, accumulating photons so faint that each individual exposure captured almost nothing. When the images were processed and stacked, 342 separate exposures layered on top of each other, the result was one of the most reproduced photographs in the history of science. The Hubble Deep Field. In that tiny, supposedly empty patch of sky, the telescope had found roughly 3,000 galaxies. Not stars, galaxies, each one containing billions of stars of its own. Some of them were close enough to show spiral structure, their arms trailing gracefully through intergalactic space. Others were so distant that they appeared as faint red smudges, their light having travelled for more than 10 billion years to reach the detector. And the distant ones, the ancient ones, the ones that existed when the universe was a fraction of its present age, were, on average, brighter and more actively forming stars than the galaxies nearby. That observation did not by itself prove that the universe was slowing down. A single image, no matter how beautiful, is a snapshot, not a timeline. But the Hubble Deep Field did something equally important. It demonstrated that looking far away is the same as looking back in time. Light travels at a fixed speed, 299,792 kilometers per second, a number that sounds fast until you consider that the nearest large galaxy is 2.5 million light-years away. Every photon that reaches a telescope carries information not about the universe as it is, but about the universe as it was at the moment that photon was emitted. A galaxy 10 billion light-years away is a galaxy as it looked 10 billion years ago. And by comparing galaxies at different distances, different epochs, astronomers could, for the first time, reconstruct the star formation history of the entire cosmos. This is precisely what Piero Madau set out to do. In 1996, working with data from the Hubble Deep Field and its successor observations, Madau published one of the earliest attempts to measure the cosmic star formation rate density as a function of redshift. The idea was straightforward in principle, though brutal in practice. Measure the ultraviolet luminosity of galaxies at various distances, correct for dust absorption, convert the luminosity to a star formation rate using known physics, and plot the result against cosmic time. The correction for dust alone was a source of years of debate, because young stars are born inside dense clouds of gas and dust that absorb their ultraviolet light and re-emit it in the infrared, meaning that a naive UV measurement will always undercount the true rate of star formation. It took a generation of infrared and submillimeter telescopes, Spitzer, Herschel ground-based arrays in the Atacama Desert, to fill in the missing piece. By 2014, when Madau and Dickinson published their comprehensive review, the picture had converged. The star formation rate density of the universe rose steeply during the first few billion years, driven by the gravitational collapse of vast hydrogen clouds into the first galaxies. It reached a broad maximum around redshift 2, 10 billion years ago, and then began a long, exponential decline that continues to the present day. The shape of the curve is remarkably clean. It does not oscillate, it does not plateau. After the peak, the decline is steady and relentless, and the best fit model describes it as an exponential with an E-folding timescale of 3.9 billion years. This means that every 3.9 billion years, the universe's rate of producing new stars drops by a factor of roughly 2.7. The rate today is somewhere between 3 and 5% of what it was at the peak. There is a way to make those numbers feel less abstract. Consider the Milky Way, a fairly typical spiral galaxy, neither unusually active nor unusually quiet. At the peak of cosmic star formation, a galaxy like ours would have been producing stars at a rate of perhaps 20 to 50 solar masses per year. Today, the Milky Way converts roughly 1 to 2 solar masses of gas into new stars annually. That is not a gentle decline. That is a factory running on a skeleton crew, burning through its last reserves of raw material, with no resupply convoy on the horizon. And Madau's review contained another number that deserves to be heard slowly because it carries more weight than its dry phrasing suggests. Half of all the stellar mass that exists in the observable universe today, half of every star in every galaxy you could ever point a telescope at, was already formed before redshift 1.3, which corresponds to roughly 9 billion years ago. 3/4 of all stellar mass was in place before the universe reached half its current age. The production has not stopped entirely, but the great majority of the work is done. The universe built most of its stars in a concentrated burst of activity that lasted a few billion years, and it has spent the 10 billion years since then slowly winding down. If you mapped this onto a human life, a crude analogy, but an honest one, you would not say the universe is middle-aged. You would say it peaked at 22 and it is now 57, and the energy it had in its 20s is not coming back. The bones still work, the lights are still on, but the sprint is over, and what lies ahead is a long, slow walk into evening. What Madau's graph does not show, what it cannot show because it is based on observational data that only extends to the present epoch, is where the curve goes from here. The exponential decline has been measured over the last 10 billion years, and there is no physical reason to expect it to reverse. The fuel is finite. The mechanisms that suppress star formation, the consumption of cold gas, the expulsion of gas by stellar winds and black hole feedback, the slow strangulation of galaxies as the expanding universe cuts off their supply lines, are all still operating. If anything, they are intensifying. The expansion of the universe is accelerating, driven by whatever dark energy is, which means that the distances between galaxy clusters are growing faster with every passing billion years. Gas that might once have fallen into a galaxy from the intergalactic medium is now being carried away by the expansion of space itself. The Madau plot, in other words, is not a complete story. It is the first half of a story, the half we can see because we are lucky enough to live in an era when the evidence is still visible. The second half is written in physics, not in data, and it says the same thing the first half says, only quieter and for much, much longer. Somewhere in the next few trillion years, a span of time so large that the entire 13.8 billion year history of the universe so far would be a rounding error within it. The last star-forming regions will exhaust their molecular hydrogen, the last nebula will collapse, the last protostar will ignite, burn through its fuel on whatever timescale its mass allows, and go dark, and after that, no new star will ever form again. Not because something prevents it, but because there is nothing left to form from. The curve reaches zero. And what lies below zero, what fills the space after the last star, is a question that requires a different kind of vocabulary entirely. Not the language of birth rates and luminosity functions, but the language of remnants, of cooling, of timescales so extreme that the word year begins to lose its meaning. Because the universe does not end when the stars go out, it only gets quieter. "10 billion years ago, the universe was on fire. Not literally. There were no flames, no oxygen to sustain combustion, no surfaces to burn. But if you could somehow compress the state of the cosmos at redshift 2 into a single image, fire would be the closest word in any human language. Galaxies were ablaze with star formation. Clouds of molecular hydrogen, some of them spanning tens of thousands of light years, were collapsing under their own gravity and fragmenting into knots dense enough to ignite thermonuclear fusion. In the most active regions, stars were being born in clusters of thousands, their combined ultraviolet radiation carving cavities in the surrounding gas, which would then cool, collapse, and form still more stars. It was a chain reaction on a cosmic scale, and it was happening everywhere, in spirals, in irregulars, in the chaotic proto-galaxies that had not yet settled into the shapes we recognize today. The numbers from that era are difficult to reconcile with the universe we inhabit now. A galaxy comparable in mass to the Milky Way during the peak of cosmic noon might have been converting 30, 50, in extreme cases several hundred solar masses of gas into new stars every single year. The Milky Way today manages 1 or 2. Some of the galaxies the James Webb Space Telescope has detected at redshifts above 9, meaning they existed when the universe was less than 500 million years old, were already forming stars at rates comparable to the Milky Way's current output, compressed into regions 1,000th the size of our galaxy. Imagine a city the size of a small town producing the industrial output of a continent. That is the kind of intensity that characterized the early universe, and it did not last. The James Webb has, in fact, become a kind of window into exactly how violent and fertile that early period was. Within weeks of its first observations in 2022, astronomers found galaxies at extreme distances that appeared far too massive and far too bright to exist so early in the universe's history. The reaction in the astrophysics community was something close to alarm. Papers were published asking whether the standard cosmological model needed to be revised, whether something was fundamentally wrong with our understanding of how galaxies form. The alarm has since cooled. More careful analysis has shown that some of those galaxies harbored active black holes that made them appear brighter than their stellar mass alone would warrant. Others seem to have formed their stars in rapid, intense bursts rather than at a steady pace, flaring up for 100 million years, then falling quiet, then flaring again. The standard model, it turns out, is probably not broken, but the data still tells us something striking. The early universe was wilder, more productive, and more extreme than almost anyone had predicted. The star formation factory was running at a capacity we had underestimated, and then it began to close. The decline did not happen because the universe ran out of hydrogen. Hydrogen is the most abundant element in the cosmos, and vast reservoirs of it still exist in the spaces between galaxies. The intergalactic medium, a diffuse web of gas threaded through the large-scale structure of the universe like dew on a spider's web. The problem is not that the hydrogen is gone. The problem is that it can no longer reach the places where stars are made. Star formation requires cold, dense molecular gas, hydrogen that has cooled to temperatures low enough to collapse under its own gravity. In the early universe, galaxies were embedded in rivers of gas flowing inward along the filaments of the cosmic web, feeding them continuously with fresh material. This is how galaxies grew so quickly and formed stars so prolifically. They were being fed. But several mechanisms, operating simultaneously and reinforcing each other over billions of years, have gradually severed those supply lines. The first is simple consumption. Galaxies used their gas. The most massive galaxies burned through their reserves earliest, converting enormous quantities of hydrogen into stars during cosmic noon and leaving themselves with depleted tanks by the time the universe was 5 or 6 billion years old. These are the galaxies astronomers describe as red and dead, massive, elliptical, full of old red stars, and almost completely devoid of the cold gas needed to form new ones. The second mechanism is feedback. Stars do not form quietly. The most massive stars, the ones that burn hottest and die youngest, explode as supernovae within a few million years of their birth, sending shockwaves through the surrounding gas that can heat it, disperse it, or blow it out of the galaxy entirely. And at the centers of most large galaxies, supermassive black holes grow by accreting gas from their surroundings. And in the process they release jets of energy so powerful that they can heat the gas in the entire galaxy and even the gas beyond it in the surrounding halo to temperatures where it can no longer cool and collapse. This is what astrophysicists call AGN feedback, the galaxy's own central engine acting as a thermostat, preventing the gas from reaching the conditions needed for star formation. It is as if the factory's furnace, by the heat of its own operation, made the raw materials too hot to work with. The third mechanism is the one that carries the most weight for the long-term future, and it is the one over which nothing in the universe has any control. The expansion of space itself is accelerating. Since the late 1990s, since the discovery that distant supernovae are receding faster than expected, implying that some form of energy inherent to empty space is pushing the universe apart, we have known that the cosmic expansion is not slowing down under gravity, as most physicists had assumed, but speeding up. This acceleration has a direct and irreversible consequence for the gas supply of galaxies. Filaments of the cosmic web that once channeled gas inward are being stretched and thinned. Gas that might have fallen into a galaxy from the intergalactic medium a few billion years ago is now being carried away by the expansion faster than gravity can pull it back. The rivers are drying up, not because something dammed them, but because the landscape itself is stretching apart. Astrophysicists have a word for what happens to a galaxy when its gas supply is cut off, but it continues to form stars from whatever internal reserves remain. They call it strangulation. The galaxy is not killed suddenly. It is slowly deprived of the material it needs to sustain itself, and over hundreds of millions of years, star formation dwindles and eventually stops. The galaxy does not explode or collapse. It simply fades. Its youngest, brightest stars die first. The blue supergiants, the O-type stars, the ones that burn through their hydrogen in a few million years. Then the yellow stars go, then the orange ones. And eventually, all that remains are the long-lived red dwarfs and the cooling remnants of everything that came before. White dwarfs, neutron stars, black holes. A galaxy that was once a furnace becomes a graveyard, still full of objects, still massive, still bound together by gravity, but no longer producing anything new. This is where the Milky Way is headed. Not tomorrow, not in 1,000 years, not in 1,000,000. But the trajectory is set, and the gas gauge is not climbing. Our galaxy still has enough molecular hydrogen to sustain modest star formation for perhaps another few billion years, long enough by coincidence for the Sun to exhaust its own hydrogen and swell into a red giant. But on the timescale of the cosmos, a few billion years is a short reprieve. The Milky Way will form its last star, and when it does, the universe's most common galaxies, the ones like ours, the spirals, the ones that looked so permanent in every photograph, will have joined the red and dead. Cosmic noon was not a beginning, it was a peak, a brief, concentrated era of maximum output, powered by conditions that no longer exist and cannot be recreated. The gas has been consumed, expelled, heated, or stretched beyond reach. The mechanisms that built the stars are the same mechanisms that, over time, shut the process down. Creation carried within it the seeds of its own exhaustion, and the exhaustion, once begun, does not reverse. It simply continues, deeper, slower, quieter, until the concept of a new star becomes not just rare, but physically impossible. Somewhere right now in a dense molecular cloud in one of the Milky Way's spiral arms, a knot of hydrogen is collapsing. It may take another 100,000 years for it to reach the temperature and pressure needed to ignite fusion. When it does, it will become a star, one of the last few billion this galaxy will ever produce. It will not know that it is late. It will burn as brightly as its mass allows, for as long as its fuel lasts, and from its surface, the universe will look exactly the way it always has, full of light and distance and time. But the era that made its birth possible is ending, and the stars that come after it will be fewer and fainter and further apart until the furnaces that once filled every corner of the sky with light have gone cold one by one, and the galaxy settles into a silence that, from the perspective of cosmic time, will last forever. Proxima Centauri is the closest star to our Sun, and you have never seen it. This is not because it is hidden behind a dust cloud or lost in the glare of a brighter neighbor. It is because Proxima Centauri, despite being only 4.24 light-years away, close enough that its light reaches us in the time it takes a child to finish primary school, is so intrinsically faint that it is invisible to the naked eye. You would need a reasonably good telescope just to find it, and even then it would appear as an unremarkable red point among thousands of brighter stars. Its luminosity is roughly 1/6 of 1% of the Sun's. If you replace the Sun with Proxima Centauri tomorrow morning, the Earth would freeze solid within hours. Noon would look like deep twilight, and the sky would carry a dim, blood-colored glow where the Sun used to be. Proxima Centauri is a red dwarf, a class of star so common that it accounts for roughly 3 out of every 4 stars in the Milky Way. Some estimates push that fraction higher, toward 80 or 85%. They are the most numerous objects in the stellar census by an enormous margin, and yet they are so faint that not a single one is visible from Earth without optical aid. Every star you have ever seen with your bare eyes, every point of light in Orion, every star in the Big Dipper, every component of the Southern Cross, belongs to the luminous minority. The red dwarfs, which outnumber them all, burn in obscurity. This obscurity is not a defect. It is, in a very precise sense, the reason they will outlast everything else in the universe. A star's lifespan is governed by a brutal trade-off between its fuel supply and the rate at which it spends that fuel. Massive stars, the blue supergiants, the O-types, the kind that dominate the visible sky, contain enormous reserves of hydrogen, but they burn through it with spectacular profligacy. A star 20 times the mass of the Sun might exhaust its core hydrogen in 5 or 6 million years, a span of time so brief by cosmic standards that it barely registers. These stars live fast, die in supernova explosions, and leave behind neutron stars or black holes. They are the fireworks of the galaxy, brilliant, brief, and gone. Red dwarfs occupy the opposite extreme. A red dwarf with 1/10 the mass of the Sun contains far less hydrogen in absolute terms, but its core temperature and pressure are so much lower that the rate of fusion is reduced by a factor far greater than the reduction in fuel. The result is a star that sips where the Sun gulps, that maintains a slow, steady burn where massive stars rage and collapse. And red dwarfs possess a structural advantage that no other class of main sequence star can match. They are fully convective. In the Sun, energy transport divides the interior into distinct zones, a radiative core where photons bounce from particle to particle across hundreds of thousands of years, and an outer convective layer where hot plasma rises and cool plasma sinks. Only the hydrogen in the core participates in fusion, which means the Sun will burn through roughly 10% of its total hydrogen supply before it leaves the main sequence. The other 90% sits in the outer layers, untouched, like fuel in a tank with no pipe to the engine. Red dwarfs have no such barrier. Convection reaches all the way from the surface to the center, continuously circulating fresh hydrogen into the fusion zone and carrying helium byproducts outward. The entire star is the engine. Every atom of hydrogen eventually passes through the core. This means a red dwarf does not waste 90% of its fuel the way the Sun does. It uses nearly all of it over a time span that makes the age of the universe look like an opening act. The numbers are staggering, and they deserve to be stated plainly. A red dwarf with about 16% of the Sun's mass, roughly the mass of Barnard's star, the fourth closest star system to Earth, will remain on the main sequence for approximately 2.5 trillion years. Not billion, trillion, 2,500 billion years. The universe is currently 13.8 billion years old, which means Barnard's star, if it were born today, would still be shining when the universe reaches an age 180 times its present value. After that, it would spend another 5 billion years as a blue dwarf, a theoretical late-stage phase in which the star contracts, heats up, and briefly achieves a luminosity about a third of the Sun's. And then, finally, it would cool into a white dwarf and fade. The smallest red dwarfs, the ones just barely massive enough to sustain hydrogen fusion, hovering near the boundary that separates true stars from brown dwarfs, could burn for 10 trillion years, 10,000 billion years. Greg Laughlin, one of the astrophysicists who calculated these lifespans, has noted that the longevity of the lowest mass red dwarfs exceeds the current age of the universe by a factor of roughly 1,000. No red dwarf in the observable universe has yet completed its life cycle. Not one. The universe is simply too young. Every red dwarf ever born is still on the main sequence, still fusing hydrogen, still burning. The late stages of red dwarf evolution, the blue dwarf phase, the final contraction into a white dwarf, exist only in computer simulations. Nature has not yet performed this experiment. The universe has not been running long enough to produce a single finished red dwarf, which means that everything we think we know about how these stars die is inference, extrapolation, and physics. No one has seen it happen. There is something quietly unsettling about that. We live in a cosmos that contains objects whose lifespans are so much longer than the age of the universe itself that we cannot observe their full evolution, only their beginning. It would be as if the only butterflies ever studied were caterpillars, and everything we knew about wings came from models. The models are good, the physics is well understood, but the empirical confirmation will not arrive for trillions of years, long after every telescope and every astronomer and every civilization that built them has been gone. And yet these dim, invisible, unremarkable stars will be the last sources of light the universe ever produces. When the massive stars have exploded and their remnants have cooled, when the sun-like stars have swelled into red giants and shed their outer layers and contracted into white dwarfs, when every blue and yellow and orange point of light has gone dark, the red dwarfs will still be there, faint, patient, burning their hydrogen one atom at a time in a universe that is growing emptier and colder around them with every passing eon. They will be the final campfires in a forest that is slowly filling with night, and their light will be so dim that you would need to be standing on a planet in orbit around one to see it at all. If you were standing on such a planet, circling a low-mass red dwarf in the deep future, trillions of years from now, the sky above you would be unrecognizable. The other galaxies would be gone, carried beyond the cosmological horizon by the accelerating expansion. The Milky Way itself, or whatever merged remnant it had become, would be a sparse collection of dead stars and dim red points, scattered so far apart that most of the sky would be pure black. Your star, your faint, red, ancient star, would be one of the last operating fusion reactors in the observable universe, and it would give you almost nothing, a dim, ruddy light, enough to cast faint shadows on the ground, not enough to read by. A permanent, unchanging dusk that lasts for billions upon billions of years, so constant that the concept of daytime would have no meaning because the light never strengthens and never fades. And then, eventually, after a span of time so long that human language has no honest way to describe it, after trillions of years of steady, faithful, almost imperceptible burning, that star too would exhaust the last of its hydrogen. The core would contract. The surface would heat and brighten briefly, for a few billion years, in the blue dwarf phase that no one has ever seen, and then it would cool and shrink and darken and join the ranks of the white dwarfs, the stellar dead, the slowly cooling embers of a fire that once lit the universe. After that, no new light, no fusion, no warmth. The stelliferous era, the age of stars, the age that Adams-Laughlin defined as the period during which the universe contains functioning nuclear furnaces, would be over, and the number that marks its end is 10 to the power of 14 years, 100 trillion years, a number that sounds large until you learn what comes after it. 100 trillion years is a number that the human mind accepts without understanding. You can write it down, a 1 followed by 14 zeros, and you can say it out loud and nod as though the information has registered, but no part of your cognitive architecture is equipped to feel the difference between 100 trillion years and, say, 50 trillion or 500 trillion. These are numbers beyond instinct. They exist only as notation. And yet 100 trillion years is where the familiar universe ends. That is the upper boundary of the stelliferous era, the age of stars, the only era in the history of the cosmos during which nuclear fusion has operated, during which light has been generated from hydrogen, during which the sky, from any vantage point, has contained points of brightness, everything that has ever happened in the universe as we understand it. The formation of galaxies, the birth and death of stars, the condensation of planets, the emergence of chemistry and biology and consciousness has occurred within this single era. And this era, in the full scope of what is coming, occupies a sliver of time so thin that it is almost invisible. In 1999, 2 astrophysicists at the University of Michigan and the University of California set out to write the biography of the universe from beginning to end. Fred Adams and Greg Laughlin were not interested only in the past, or in the next few billion years, or even in the next trillion. They wanted to know what happens all the way to the end, and whether the end is even a coherent concept for a universe that may expand forever. The result was a book called The 5 Ages of the Universe, and its most lasting contribution was a framework that divided the entire timeline of the cosmos into 5 distinct epochs, each defined by the dominant source of energy and the dominant type of structure. The framework uses a logarithmic timescale, which is the only sane way to discuss durations that span more than 100 orders of magnitude. Instead of counting in years, Adams and Laughlin count in cosmological decades, where cosmological decade n corresponds to 10 to the power of n years. The present moment, at 13.8 billion years after the Big Bang, falls just above cosmological decade 10. The stelliferous era runs from cosmological decade 6 to cosmological decade 14. Written in plain numbers, that is from 1 million years to 100 trillion years, a range that includes the birth of the first stars, the age of galaxies, and everything you or anyone you have ever known has experienced. It is also, by a crushing margin, the shortest of the 5 ages. The second era, the degenerate era, runs from cosmological decade 15 to cosmological decade 39. Those numbers look deceptively close to 14, as though we are talking about a period only modestly longer than the Stelliferous era. We are not. Each step on the logarithmic scale represents a factor of 10. Cosmological decade 15 is 10 times longer than cosmological decade 14. Cosmological decade 20 is 100,000 times longer. Cosmological decade 39, the end of the degenerate era, is 10 to the 25th power times longer than the end of the Stelliferous era. That is 10 million billion times longer. The degenerate era, the era of cooling stellar remnants and slowly decaying matter, lasts so much longer than the age of stars that any comparison between the two collapses into meaninglessness. It is not like comparing a day to a year. It is like comparing a single heartbeat to the entire history of the Earth and then multiplying the difference by 1 billion. And the degenerate era is not even the longest one. The third era, the black hole era, runs from cosmological decade 40 to cosmological decade 100. 100 zeros after the 1, a googol of years. During this era, the only organized structures remaining in the universe are black holes, and they are not permanent either. They are slowly evaporating through a quantum mechanical process that we will return to later. The black hole era is so long that the degenerate era, which was already incomprehensibly longer than the Stelliferous era, becomes a rounding error within it. And the fourth era, the dark era, begins at cosmological decade 101, and it does not end. It cannot end because there is nothing left to end. No structures, no energy gradients, no processes, no change. The dark era is not a period of time in the way that the other eras are periods of time. It is the state that the universe settles into when every process that could generate change has been exhausted. It is the universe at maximum entropy, at thermal equilibrium, at a temperature asymptotically approaching absolute zero, and it lasts forever. Not for a googol of years or a googolplex or any number you could write with all the atoms in the observable universe as ink. It lasts for an infinite duration, which is not a very long time, but a categorically different kind of time, a time with no end and no structure and no events to distinguish one moment from the next. Adams and Laughlin understood what they were describing. In the preface to their book, they acknowledged that the far future of the universe is speculative, dependent on physics that may be incomplete, and that nature has a long track record of surprising physicists who thought they had the final answer. But within the framework of known physics, general relativity, quantum mechanics, thermodynamics, the standard model of particle physics, the trajectory is clear. The universe begins hot, dense, and structured. It expands, cools, and builds increasingly complex systems, atoms, molecules, stars, planets, life. And then, on a timescale that dwarfs the era of complexity by factors beyond comprehension, it disassembles everything it built and returns to a state of featureless uniformity. What Adams and Laughlin's framework makes viscerally clear, in a way that raw numbers alone do not, is the position we occupy within this timeline. We are not in the middle. We are not even close to the middle, because there is no middle of an infinite timeline. We are at the very beginning, in the first fraction of the 1% of the Stelliferous era, which is itself the briefest of the 5 ages. The entire 13.8 billion year history of the universe, from the Big Bang to this conversation, represents a cosmological instant. Everything we know, everything we have ever built or discovered or imagined, has taken place in a flicker at the opening of a story that will run, in one form or another, for longer than any number can express. There is a way to make this feel less like abstraction and more like vertigo. Imagine the entire Stelliferous era, all 100 trillion years of it, from the first star to the last, compressed into a single day. Dawn is the Big Bang. The first stars ignite at 6 in the morning. Cosmic noon falls around 9:30. The sun forms sometime in the early evening, around 5 o'clock. And the present moment, right now, the moment you are hearing this, is about 8 minutes past 5. The whole of human history, from the first stone tools to the latest satellite launch, fits into the last 0.003 of a second before the current time. The rest of the day, all those hours stretching ahead to midnight, is the slow dimming of the final stars. That is the Stelliferous era. Now imagine that single day, dawn to midnight, as the first page of a book. The degenerate era is the next 10 million billion pages. The black hole era is everything after that, for a Google more pages. And the dark era is a library with no walls, filled with blank pages, extending in every direction, without end. We are 8 minutes past 5 on the first day, on the first page of a book with no last page. And the 5 ages are not a metaphor. They are not a poetic conceit or a philosophical framing designed to make you feel small. They are the output of physics applied to cosmology, run forward in time with the best models available and checked against every observation we can make. They may be wrong in their details. Physics has been wrong before and will be again. But the broad shape of the trajectory is constrained by thermodynamics, and thermodynamics does not negotiate. Entropy increases, energy disperses, structure degrades, and given enough time, and the universe has nothing if not time, every organized system eventually dissolves into the background. The question that Adams and Laughlin could not answer, the question that their framework raises but cannot resolve, is what the intermediate stages look like. They told us the chapter titles, they told us the durations, but they did not and could not describe every page. What happens to matter when the stars are gone? What happens to the remnants when the protons that compose them begin to decay? What happens to the black holes when there is nothing left to feed them and the slow leak of Hawking radiation becomes the only process still operating in the universe? Those questions require their own answers, and the answers are stranger than the framework that contains them. When the last red dwarf exhausts its hydrogen and contracts into a white dwarf, sometime around cosmological decade 14, 100 trillion years from now, the universe will not go dark all at once. There will be no moment of extinction, no final sunset watched from a final planet. The transition is gradual in the way that winter is gradual. You do not notice the days shortening until one evening you realize the light is gone and you cannot say exactly when it left. What remains after the last fusion reactor shuts down is a universe still full of objects. Trillions upon trillions of them, scattered across the expanding volume of space, each one a remnant of something that once burned. White dwarfs, the compressed cores of dead sun-like stars, roughly the size of the Earth but with the mass of the Sun, made primarily of carbon and oxygen packed into a crystalline lattice so dense that a teaspoon of it would weigh several tons. Neutron stars, the collapsed remnants of more massive stars, city-sized spheres of matter so compressed that their density rivals that of an atomic nucleus, where a sugar cube-sized sample would outweigh Mount Everest. Brown dwarfs, objects that never quite achieved the core temperature needed to sustain hydrogen fusion, failed stars that have been cooling slowly since the moment they formed, and black holes, the gravitational scars left behind by the most massive stars, objects from which no information escapes and around which space-time itself is bent into configurations that general relativity can describe but the human imagination struggles to picture. This is the census of the degenerate era, a cosmos populated entirely by the dead and the failed, drifting through an expanding void, radiating the last of their stored heat into a space that grows colder with every passing eon. White dwarfs dominate the early stages of this era, and their story is one of the slowest processes in all of physics. A newly formed white dwarf, fresh from the death of its parent star, its outer layers blown away in a planetary nebula, begins its existence with a surface temperature of perhaps 100,000 Kelvin, hot enough to glow brilliant blue-white. But with no internal energy source, no fusion, no gravitational contraction significant enough to matter, the white dwarf has nothing to do except radiate its stored thermal energy into space and cool, and it does, but at a rate that would test the patience of geology. The cooling timescale of a white dwarf depends on its mass, its composition, and the opacity of its thin atmosphere, but for a typical carbon-oxygen white dwarf of about 0.6 solar masses, the numbers are well constrained by theoretical models. After 1 billion years, its surface temperature has dropped to roughly 5,000 or 6,000 Kelvin, about the temperature of the Sun's surface. After 10 billion years, a span comparable to the current age of the universe, it has cooled to perhaps 3,000 or 4,000 Kelvin, a dull reddish glow, the color of a cooling ember. After 100 billion years, it has faded to under 1,000 Kelvin, dimmer than any star visible to the naked eye, radiating primarily in the infrared, and the cooling continues, slower and slower as the temperature drops, because a cooler object radiates less energy per unit time, which means it loses heat more slowly, which means the cooling itself decelerates. The curve is asymptotic. The white dwarf approaches absolute zero, but never reaches it, and the time required to cool to any given temperature grows longer the closer it gets. The end point of this process has a name, though it is a name for something that does not yet exist anywhere in the observable universe. A white dwarf that has cooled to the point where it no longer emits any detectable radiation, a dead dark cold sphere of crystallized carbon and oxygen, is called a black dwarf. It is a theoretical object in the strictest sense. The universe is 13.8 billion years old, and the time required for even the oldest white dwarfs to cool to black dwarf temperatures is estimated at somewhere between 10 to the 15th and 10 to the 25th years, depending on the model. No black dwarf has ever formed. None will form for eons. The universe has not been running long enough to produce even one. Think about what that means. The final state of 97% of all stars that have ever lived, the white dwarf to black dwarf cooling track, has never been completed. We know how it begins because we can observe white dwarfs at various stages of cooling. We know from physics how it must end. But nature has not yet finished a single one of these objects. The cosmos is, in this specific and measurable sense, still too young to have produced its own dead. And the black dwarfs, once they form, will persist. For how long depends on a question that physics has not yet settled. Do protons decay? The standard model of particle physics does not require protons to be unstable. A proton in the standard model can last forever, but most grand unified theories, the theoretical frameworks that attempt to merge the strong, weak, and electromagnetic forces into a single description, predict that protons do eventually decay with a half-life somewhere above 10 to the 34th years. The most sensitive experiment ever conducted to test this prediction is Super Kamiokande, a detector buried deep inside a mountain in Japan, consisting of 50,000 tons of ultra-pure water surrounded by 11,000 photomultiplier tubes, each one waiting to catch the faint flash of Cherenkov radiation that would signal a proton falling apart. After decades of observation, Super Kamiokande has not detected a single proton decay event, which places the half-life above 10 to the 34th years. But it does not rule out decay at longer timescales. The experiment has established a floor, not a ceiling. If protons do decay, and most theorists expect that they do, though no one can say with certainty, then the consequences for the degenerate era are absolute. Every object made of baryonic matter, every black dwarf, every neutron star, every cold brown dwarf, every rogue planet, every grain of dust, will slowly, imperceptibly disintegrate. A proton decaying produces a positron and a neutral pion, which itself decays almost instantly into two gamma-ray photons. One by one, over timescales of 10 to the 36th or 10 to the 40th years, the atoms that make up these objects will come apart. A black dwarf losing its protons would not shatter or collapse. It would simply become less massive, emitting a faint trickle of gamma radiation and positrons, growing lighter and smaller over spans of time that make the age of stars look like a camera flash. Eventually, after enough protons have decayed, the object would lose structural coherence and dissolve into a diffuse cloud of leptons and photons, indistinguishable from the background radiation of the universe. If protons do not decay, if the standard model is correct and protons are truly stable, then the fate of matter is different, but no less strange. Freeman Dyson, among others, has calculated that on timescales of 10 to the 1500th years, quantum tunneling would gradually rearrange the nuclei inside a black dwarf into iron 56, the most stable nuclear configuration. The entire object would, given enough time, transmute itself into a sphere of iron through a process so slow that the word process barely applies. And then, on still longer timescales, that iron sphere would quantum tunnel into a black hole and evaporate. Either way, through proton decay or through quantum tunneling, matter does not survive. The question is not whether it disintegrates, but when and by which mechanism. The degenerate era is not a period of darkness in the way that a power outage is darkness. A power outage is temporary, and you know the lights will come back on. The degenerate era is darkness that settles in and deepens. Objects that once were stars are cooling toward absolute zero. Atoms that once were stable are coming apart, and the expansion of the universe continues, stretching the distances between these remnants, diluting the density of matter, ensuring that even if some unlikely process could reignite fusion or reverse the decay, there would not be enough material in any one place to make it matter. What fills the degenerate era is not events, but durations, not things happening, but things slowly ceasing to exist. It is an era measured not in what occurs, but in what is gradually subtracted: heat, structure, coherence, matter itself, until the universe has been simplified to its barest components: scattered photons, lonely leptons, and the gravitational wells of objects that will define the next era entirely. Black holes, the last things in the universe with any claim to structure, and even they are not permanent. In January 1973, a 31-year-old English physicist travelled to Moscow to meet a man whose work he disagreed with. Stephen Hawking had been thinking about black holes for several years. They were, at that point, still largely theoretical objects, predicted by general relativity but not yet observed with any confidence, and he had become interested in the question of whether black holes could be said to have a temperature. The conventional answer was no. A black hole was, by definition, an object from which nothing escaped. It absorbed everything: light, matter, radiation, and emitted nothing. Its temperature, in any physically meaningful sense, was zero. Jacob Bekenstein, a graduate student at Princeton, had recently argued otherwise. Bekenstein proposed that black holes possess entropy, that they are not simple, featureless objects, but thermodynamic systems with a measurable disorder proportional to the surface area of their event horizon. Hawking found the idea irritating. Entropy implies temperature, and temperature implies radiation, and a black hole that radiates is a black hole that leaks, which contradicts the defining property of a black hole. Hawking traveled to Moscow partly to discuss this problem with Yakov Zeldovich and his student Alexei Starobinsky, who had proposed that rotating black holes might create and emit particles through a quantum process analogous to the radiation emitted by a spinning metal sphere. Hawking was skeptical of their calculation but intrigued by the underlying idea. What happened over the following months is one of the most celebrated sequences in the history of theoretical physics. Hawking returned to Cambridge and set about trying to prove Bekenstein wrong, to demonstrate that black holes do not, in fact, have a temperature, and that Bekenstein's entropy was a mathematical analogy rather than a physical reality. Instead, he proved Bekenstein right by applying quantum field theory to the curved space-time around a black hole's event horizon. Hawking discovered that the vacuum itself, what appears to be empty space, is not truly empty in the vicinity of extreme gravity. Quantum fluctuations near the event horizon produce pairs of virtual particles, and the geometry of space-time around the black hole ensures that, in some fraction of cases, one particle of the pair falls inward while the other escapes outward. The escaping particle carries positive energy. The infalling particle, from the perspective of an outside observer, carries negative energy, which means it reduces the mass of the black hole by a tiny amount. The net effect is that the black hole emits a faint, steady stream of thermal radiation, as though it were a hot body with a temperature inversely proportional to its mass. Hawking published his result in a brief paper in Nature in March 1974 under a title that read more like a tabloid headline than a physics abstract. Black hole explosions? The question mark was important. What Hawking had shown was not merely that black holes radiate, it was that they evaporate. Each emitted particle removes a small amount of mass from the black hole, and as the black hole loses mass, its temperature rises, which increases the rate of emission, which accelerates the loss of mass. The process is a feedback loop, vanishingly slow at first but quickening over time, until in the final moments the black hole erupts in a burst of high-energy radiation and ceases to exist. The timescales involved are, even by the standards of this story, staggering. A black hole with the mass of our Sun, roughly 2 × 10⁻30 kilograms, would take approximately 10 to the 67th years to evaporate completely. Written out, that is a 1 followed by 67 zeros. The current age of the universe is 10 to the 10th years. The sun mass black hole would need to evaporate for a duration roughly 10 to the 57th times longer than the universe has existed. You could rerun the entire history of the cosmos, from the Big Bang to this sentence, 10 trillion times, end to end, and the black hole would still be there, barely diminished, its Hawking radiation so faint that it would be immeasurably colder than the cosmic microwave background. And that is a small black hole. Sagittarius A star, the supermassive black hole at the center of the Milky Way, has a mass of roughly 4 million suns. Its evaporation time is approximately 10 to the 87th years. The largest known black holes, the ultra-massive objects at the centers of giant elliptical galaxies, with masses of tens of billions of solar masses, would take on the order of 10 to the 100th years to evaporate. A Google. That number, 10 to the 100, is the one that defines the outer boundary of the black hole era, the point at which the last black hole in the observable universe emits its final quantum of radiation and vanishes. There is a detail about Hawking radiation that popular accounts often get wrong, and the correction matters for understanding what the death of a black hole actually looks like. The image that most people carry, two particles appearing at the event horizon, one falling in, one escaping, is a pedagogical simplification that Hawking himself used but later acknowledged was not a precise description of the underlying physics. The actual mechanism involves the distortion of quantum vacuum states by the curvature of space-time, and the radiation is not emitted from the event horizon itself, but from a region around the black hole known as the photon sphere, where the effective radiating surface is several times larger than the horizon area. The details were worked out in 1976 by Don Page, then a student of Hawking's, who calculated the precise power output and lifetime for non-rotating black holes and established the cubic relationship between mass and evaporation time that is still used today. But the intuitive picture, a slow, steady leak of energy from an object that was supposed to be permanent, is essentially correct, and the most unsettling aspect of it is not the mechanism but the implication. Black holes were the last objects in the universe with any claim to structure, the last concentrations of mass energy in a cosmos that has been dispersing and diluting everything else for eons. When the black holes go, there is nothing left that could reasonably be called a thing. No stars, no planets, no atoms, no remnants. Only radiation, photons and gravitational waves and whatever particles Hawking radiation produces, spreading through an expanding void, growing colder and more diffuse with every passing moment. The final stages of a black hole's life would be, if anyone were present to observe them, the most dramatic events remaining in the universe. As the black hole shrinks, its temperature climbs. A solar mass black hole, for most of its 10 to the 67th year lifespan, has a temperature of about 60 billionths of a Kelvin, colder than the cosmic microwave background, colder than anything in the present-day universe. But in its final seconds, as its mass plummets and its temperature soars, it becomes extraordinarily hot, hotter than the center of a star, hotter than the cores of the earliest galaxies, hotter than anything that has existed since the first fraction of a second after the Big Bang. In the last tenth of a second, a black hole of roughly 2 solar masses would release at least 10 to the 30th ergs of energy. A final flash of gamma radiation, a brief and brilliant scream into a universe that has long since fallen silent. No one will see it. By the time the last black holes are evaporating, the universe will have been devoid of observers for timescales so long that the entire history of life on Earth, from the first cell to the last thought, would be an undetectable flicker in the background. The gamma-ray burst will propagate outward at the speed of light through empty space, growing fainter with distance, redshifting as the universe expands, until it is indistinguishable from the thermal noise of the vacuum. A signal sent to no one, received by nothing, marking the end of the last structure the universe will ever contain. After that, there are no more events. Not in the sense that nothing interesting happens, in the sense that the conditions required for an event to occur, an energy gradient, a temperature difference, a concentration of mass, no longer exist anywhere. The universe has reached the state that thermodynamics has been pointing toward since the 19th century, the state that Lord Kelvin described in 1852 when he wrote about the progressive dissipation of mechanical energy. Every gradient has been flattened, every temperature has equalized, every structure has been dismantled by time, by expansion, by the quiet arithmetic of entropy. And what remains, what fills the silence after the last black hole's final flash, is a question that sounds simple but carries the weight of everything that has come before it. What does a universe look like when nothing is left to happen? What does time mean when there is no change to measure it by? The answer has a name. Physicists call it the Dark Era, and it is not a chapter in the universe's story. It is the space after the story ends, the blank page that runs on, without interruption, forever. Imagine a room, not a large room, just an ordinary room, sealed, insulated, with no windows and no doors. Inside the room there is a cup of hot coffee and a glass of ice water. You do not need a degree in physics to know what will happen. The coffee will cool, the ice will melt, the water will warm, and after enough time, an hour, maybe two, everything in the room will be the same temperature. The coffee will be lukewarm, the water will be lukewarm, the air will be lukewarm, and from that point on, nothing will ever change again. Not because something is preventing change, but because change requires a difference, a gradient, a gap between hot and cold, between high energy and low energy, and the room no longer contains one. The system has reached thermal equilibrium, and at equilibrium, the concept of something happening loses its meaning. That room is the universe, the coffee is the stars, the ice water is the void, and the lukewarm stillness that follows is the dark era, except the temperature is not lukewarm. It is a fraction of a degree above absolute zero, and the room is not a room, but an expanding volume of space so vast that the distance between any two remaining particles can be measured in light years, and the time between any two interactions can be measured in eons. The dark era begins, roughly, at cosmological decade 101, after the last black hole has evaporated, after the last burst of Hawking radiation has faded below detectability, after every process that could produce a measurable change in the state of the universe has run its course. What remains is not nothing in the absolute sense. The universe still contains particles, photons mostly, neutrinos, electrons and positrons, drifting through the void at velocities so low they barely qualify as motion. Gravitons perhaps, though we have never detected one and may never do so. These particles are the residue of 14 billion years of cosmic history, the cooled, diluted, red-shifted remnants of everything the universe once contained. And they are so sparse, so far apart, so low in energy, that the probability of any two of them interacting within any reasonable time frame is effectively zero. This is the state that the second law of thermodynamics has been pointing toward since 1852, when William Thomson, Lord Kelvin, first described what he called the universal tendency toward the dissipation of mechanical energy. Kelvin understood that every physical process converts some fraction of useful energy into waste heat, and that waste heat disperses and cannot be fully recovered. A steam engine loses energy to friction. A star loses energy to radiation. A black hole loses energy to Hawking radiation. And in every case, the energy does not vanish. The first law of thermodynamics ensures that, but it spreads out, becomes more uniformly distributed, and in doing so becomes less capable of doing work. Entropy increases, gradients flatten, and the arrow of time, which depends on the existence of gradients to give it direction, loses its point. There is a distinction worth drawing here because it changes the way the dark era feels when you think about it carefully. The universe at thermal equilibrium is not frozen. The particles are still moving. Quantum fluctuations still ripple through the vacuum. The laws of physics still operate with the same precision they always have. What has changed is not the rules, but the game. There is no longer any meaningful difference between one region of space and another, between one moment and the next. A physicist dropped into the dark era with perfect instruments could still measure the temperature of the cosmic background. It would be extraordinarily close to zero, but not exactly zero, because the cosmological horizon of an accelerating universe emits a faint thermal radiation of its own, the Gibbons-Hawking temperature, which for our universe works out to roughly 10 to the minus 30th Kelvin. The physicist could confirm that particles exist, that quantum mechanics operates, that space-time has a geometry. but they could not point to any direction and say, something is happening over there, or point to any moment and say, this is different from the moment before. This is what physicists mean when they say that time becomes operationally meaningless at thermal equilibrium. The equations of physics still include a time variable. The parameter still runs. But if no process distinguishes one value of that parameter from another, if the state of the system at time t is statistically indistinguishable from the state at time t plus 1 billion years, then the word time has lost its experiential content. A clock can only tick if something changes between ticks. In the dark era, nothing does. The duration of this state is not a number, it is a category. The dark era does not last for 10 to the 100 years, or 10 to the 1,000 years, or any finite quantity. It lasts forever, not as a figure of speech, but as a mathematical property of the cosmological model. In a universe dominated by a positive cosmological constant, the expansion continues without end. The temperature asymptotically approaches zero without reaching it, and there is no mechanism, no instability, no phase transition, no recurrence, that would bring the universe back to a state capable of supporting structure or change. The word forever is used in physics with extreme caution because physicists know that every model is provisional and that nature has surprised them before. But within the framework of general relativity and the standard model of particle physics, the dark era has no exit. This is where the scale of the thing resists language entirely. We have already, in previous chapters, struggled with numbers like 10 to the 67th and 10 to the 100th. Those numbers were large enough to break ordinary intuition, but they were still numbers, finite quantities that could, in principle, be written down, compared to other quantities placed on a timeline. The dark era is not a quantity, it is a condition. Asking, how long does the dark era last, is like asking, how long does the number line continue past 10 to the 100? The answer is that it does not continue for any particular distance. It continues without limit. Every number you can name, every Googleplex, every power tower, every notation that human mathematics has ever devised to describe large quantities, is past and left behind, and the dark era continues, unchanged, indifferent to the passage of time that it no longer has any use for. There are physicists who find this idea incoherent, or at least incomplete. Sean Carroll, a cosmologist at Johns Hopkins, has argued that the concept of eternal thermal equilibrium may be undermined by our incomplete understanding of quantum gravity, and that a universe that appears to have reached maximum entropy might still possess degrees of freedom that allow for further evolution in ways we cannot currently predict. Others have pointed out that the de Sitter space produced by a positive cosmological constant has a finite entropy, the Gibbons-Hawking entropy, which implies that the system is not truly at maximum entropy in the way that a classical gas in a sealed box would be. These are genuine open questions, and they may eventually lead to a picture of the far future that is less absolute than the one described here. But they are open questions in the way that the interpretation of quantum mechanics is an open question. They may change the philosophical framing without changing the observable outcome. The universe still cools, the structure still disperses, the gradients still flatten, and the timescale on which anything interesting might happen, even in the most optimistic models, is so much longer than the timescale on which structure existed that the practical difference between nothing ever happens again and something might happen in 10 to the 10 to the 10 to the 100th years is not a difference that matters to anyone who is not a mathematician. What the dark era means, not as physics, but as a fact about the universe you are lying in right now, the universe whose air you are breathing and whose starlight you can see if you walk outside, is that every structure the cosmos has ever produced is temporary. Every atom, every molecule, every crystal, every cell, every organism, every civilization, every star, every galaxy, every black hole, all of it is a transient deviation from equilibrium, a brief ripple in a system that is heading with the full weight of thermodynamics behind it toward a state of perfect featurelessness. The ripple is beautiful. The ripple contains, among other things, you. But the ripple passes, and what remains, what was always going to remain from the moment the universe began expanding and cooling, is stillness. Not the stillness of peace, because peace implies a contrast with turmoil. The stillness of completion, the stillness of a system that has done everything it is capable of doing and has nothing left. In the dark era, the universe is not dead, it is finished, and the silence that follows, infinite, featureless, without boundary or interruption, is not the silence of an empty room. It is the silence of a room that was once full, that held light and heat and complexity and motion, and that has slowly, over timescales that no mind was built to comprehend, returned every borrowed thing to the background from which it came. But we are not there yet. We are still in the bright part, the part where stars exist, where galaxies are visible, where the evidence of the universe's history is written across the sky in wavelengths we can read. And that evidence, it turns out, will not last, because the same expansion that is dimming the stars is also erasing the record of their existence, pushing the proof of the universe's own past beyond the reach of any future observer. In 1908, the prevailing scientific view of the cosmos was that the universe consisted of a single, enormous collection of stars, our galaxy, surrounded by an infinite empty void. There were no other galaxies, there was no expansion, there was no beginning. The universe was static, eternal, and alone. This was not a fringe view held by a handful of eccentric astronomers. It was the consensus, supported by the best observations available and endorsed by some of the most prominent scientists of the era. It took another 15 years until Edwin Hubble identified individual stars in the Andromeda Nebula in 1923 and demonstrated that it was a separate galaxy millions of light years away, for that consensus to collapse. In 2007, two physicists named Lawrence Krauss and Robert Scherer published a paper that should make you deeply uncomfortable. Its title was The Return of a Static Universe and the End of Cosmology, and its argument was this: if the universe continues to expand at an accelerating rate, as all current data indicates it will, then the evidence on which modern cosmology is built, the evidence for the Big Bang, for the expansion of space, for the cosmic microwave background, for the primordial synthesis of hydrogen and helium, will eventually disappear. Not because the evidence will be destroyed by some catastrophic event, but because the expansion of space itself will carry it beyond the reach of any possible observer. The pillars of modern cosmology will be removed one by the same force that allowed us to discover them, and future civilizations, if any exist, will find themselves in a universe that looks from every possible angle of observation, exactly like the static, lonely island universe of 1908. The mechanism is not speculative. It is a straightforward consequence of dark energy and the accelerating expansion it drives. Every galaxy that is not gravitationally bound to our own local group is receding from us, and the speed of that recession increases with distance. Galaxies that are far enough away are already receding faster than the speed of light, which does not violate relativity because it is space itself that is expanding, not the galaxies moving through space. The light from these galaxies is being stretched, redshifted, to longer and longer wavelengths as it travels through expanding space. And for galaxies beyond a certain distance, the expansion is so rapid that their light will never reach us, no matter how long we wait. They have crossed the cosmological event horizon, a boundary that is not a physical wall but a mathematical surface beyond which information can no longer propagate to our location. Krauss and Scherer calculated the timescales. Within about 100 billion years, roughly 7 times the current age of the universe, the redshift of all external galaxies will have exceeded 5,000. At that point, the light from those galaxies will have been stretched so far into the microwave and radio spectrum that it would be undetectable by any conceivable telescope. Within 10 trillion years, the redshift will have reached 10 to the 53rd power, a number so large that the wavelength of the light from those galaxies would exceed the size of the observable universe itself. At that point, the galaxies are not merely faint. They are, in every physically meaningful sense, gone. But the loss of visible galaxies is only the beginning of what Krauss and Scherer described. The cosmic microwave background, the faint thermal afterglow of the Big Bang, the single most important piece of evidence for the origin of the universe, will also be erased. The CMB has a current temperature of about 2.7 Kelvin, and it is already cooling as the universe expands. In 100 billion years, it will have cooled and redshifted to the point where it is indistinguishable from the quantum noise of the vacuum. A future astronomer searching for evidence of a hot, dense origin of the universe would find none, because the radiation that carries that evidence would have faded below the threshold of any possible measurement. The primordial abundance of light elements, the specific ratios of hydrogen, helium and lithium produced in the first few minutes after the Big Bang, which match the predictions of Big Bang nucleosynthesis with striking precision, would also become unreadable. Those ratios are currently observable in the spectra of the oldest, most pristine gas clouds in the universe. But those gas clouds are embedded in distant galaxies and intergalactic filaments, all of which will have been carried beyond the horizon. The local gas within our own galaxy or its merged remnant will have been processed through multiple generations of stellar nucleosynthesis, thoroughly contaminating the primordial signal. The evidence will not be hidden, it will have been overwritten. What remains in Krauss and Scherer's analysis is a single galaxy, or rather a single gravitationally bound cluster of galaxies, the merged remnant of the local group, dominated by whatever Milky has become, surrounded by an apparently infinite expanse of empty space. No other galaxies visible in any direction, at any wavelength, at any sensitivity. No expansion detectable, because there would be nothing external to measure the expansion against. No CMB, no primordial element ratios, no evidence anywhere in the observable universe that the cosmos was ever anything other than a single static island of stars in an eternal void. A civilization arising in that era, intelligent, curious, scientifically sophisticated, would look up at their sky and see exactly what astronomers saw in 1908. They would construct a model of the universe based on the available data, and that model would be wrong, not because they were bad scientists, but because the data necessary to reach the correct conclusion would no longer exist within their observable universe. They would conclude, reasonably and rigorously, that the cosmos is static and eternal, that their galaxy is all there is, and that the universe has no origin and no large-scale dynamics. And they would have no way, not even in principle, to know that they were missing anything. Krauss and Scherer, in their paper, delivered this conclusion with a line that reads like dark comedy. We live in a very special time in the evolution of the universe, the only time at which we can observationally verify that we live in a very special time in the evolution of the universe. The circularity is deliberate. We can see the expansion because we live early enough. We can measure the CMB because it has not yet faded. We can read the primordial element ratios because the gas has not yet been fully reprocessed. Every major discovery of 20th century cosmology depends on the universe being young enough, close enough to its own origin, for the evidence to remain intact. And that window is closing, not quickly, by human standards, but on the timescale of the universe, the window is a sliver, and we happen to be standing in it. There is a question that Krauss and Scherer raised but did not fully answer, and it is a question that their analysis makes almost impossible to avoid. If the universe erases its own past, if the expansion systematically removes the evidence of its own history, then how confident can we be that the evidence available to us right now is complete? We are not future observers, looking at an impoverished sky and drawing incorrect conclusions. We are present-day observers, looking at a rich, data-filled sky and drawing what we believe are correct conclusions. But Krauss and Scherer have demonstrated that there exists at least one epoch in the life of this universe during which the best possible science, conducted by the best possible scientists, leads to a fundamentally false picture of reality. The question is whether we know, truly know, that our epoch is not one of them. The standard response from cosmologists is that we have strong reasons to believe our current picture is correct and that the comparison is asymmetric. Future observers will have less data, not different data. We have the CMB, we have the galaxy redshifts, we have the primordial element ratios, we have the full dataset, and our models match it with extraordinary precision. But there is something about Krauss and Scherer's result that lingers, not as a scientific objection, but as an epistemological chill. The universe, they have shown, is not a neutral stage on which science is performed. It is an active participant, and it is gradually withdrawing the evidence. The stage is dismantling itself, and the dismantling has already begun. Some objects that were visible when the universe was half its present age are already gone, already beyond the horizon, already lost. The sky is shrinking, and the fact that it is shrinking slowly, imperceptibly, on timescales that dwarf human civilization does not change what it means. It means we are the witnesses, not the last witnesses. There may be civilizations after us for billions of years who can still see what we see, but we are among the generations for whom the universe is still legible, for whom the full story is still written across the sky in wavelengths that our instruments can read. The cosmic microwave background is still warm enough to detect. The distant galaxies are still close enough to see. The expansion is still slow enough to measure, and one by one, century by century, eon by eon, these things will fade, not because they are being destroyed, but because space itself is carrying them away, gently, silently, at an accelerating pace, until the sky is dark and the record is gone, and the universe has forgotten that it ever had a history at all. The Andromeda galaxy is moving toward us at 110 kilometers per second. This is not a guess or an approximation. It is a direct measurement derived from the blue shift of Andromeda's spectral lines, one of the very few galaxies in the observable universe whose light is compressed rather than stretched, because it is one of the very few galaxies that is actually approaching rather than receding. Everything else is moving away. Everything else is being carried outward by the expansion of space. Andromeda is falling inward, pulled by the combined gravitational mass of the local group, our small bound neighborhood of galaxies, held together against the current of cosmic expansion by the sheer weight of its own dark matter. At 110 kilometers per second, closing a gap of 2.5 million light-years, the arithmetic gives you a collision timescale of roughly 4 to 5 billion years. For most of the last decade, that number was treated as settled, a confident prediction bolstered by precise measurements of Andromeda's radial velocity from Hubble and its lateral motion from Gaia. The merger was supposed to be inevitable, two massive spirals falling into each other, their gas clouds compressing, a final starburst lighting up the merged remnant before it settles into a gas-poor elliptical galaxy that Avi Loeb, the Harvard astrophysicist who named it, called Milkomeda. The picture has recently become more complicated. In 2025, a team led by Till Sawala at the University of Helsinki published the results of 100,000 Monte Carlo simulations of the local group's gravitational dynamics, incorporating the most precise Gaia-era measurements of galaxy motions alongside the gravitational influence of objects that earlier models had treated as minor players, most significantly, the Large Magellanic Cloud. The LMC, a satellite galaxy of the Milky Way with roughly 15% of its mass, orbits on a trajectory nearly perpendicular to the Milky Way Andromeda line of approach, and its gravitational tug is enough to shift the Milky Way's trajectory by a small but consequential amount. Sawala's simulations found that the probability of a head-on collision within the next 10 billion years dropped to approximately 50%. In half of the simulations, the galaxies pass each other at a distance of roughly 500,000 light-years and enter a slow orbital decay that takes additional billions of years to complete. Then, in early 2026, a second study using updated Gaia proper motion data pushed the probability back up to roughly 90%, with a median merger time of 6.5 billion years. The science is still moving. The error bars are still large. But the broad picture, even in the most conservative models, is that the Milky Way and Andromeda will interact gravitationally within the next 10 billion years, and in the majority of outcomes, they will eventually merge into a single system. What that merger looks like, from the perspective of anyone fortunate or unfortunate enough to be present, depends on the timescale you care about. In the first few billion years of interaction, the galaxies would not collide so much as interpenetrate. The average distance between stars in a galaxy is enormous. If the Sun were a ping-pong ball, the nearest star would be a P roughly 1,100 kilometers away, which means that the chance of any two stars physically hitting each other during a galactic merger is negligible. What collides is the gas. The diffuse molecular hydrogen that fills the space between the stars, spread thin across the galactic disk, is compressed by the gravitational tides of the interaction, and that compression triggers exactly the same process that has been declining for 10 billion years. star formation. During the merger, for a brief window, perhaps a few 100 million years, the rate of star formation in the combined system would spike. New stars would ignite in compressed gas clouds, and for a geologically brief period, the merged galaxy would blaze with the kind of activity that has not been seen in this part of the universe since cosmic noon. Hot, blue, massive stars, the kind that burn through their fuel in a few million years and die in supernova explosions, would appear in clusters throughout the tidal tails and the compressed central regions. The night sky from any surviving planet would be unrecognizable, not the familiar band of the Milky Way, but a chaotic, evolving splash of light spanning the entire celestial sphere, streaked with nebulae and punctuated by new stars being born in real time on timescales short enough for a long-lived civilization to watch. It would be, by any measure, the last great spectacle the local universe has to offer, because the merger does not renew the gas supply. It compresses whatever gas remains, and by the time Andromeda arrives, the Milky Way will already have spent several more billion years consuming its reserves. The starburst is not a renaissance. It is the last withdrawal from an account that has been draining for 10 billion years. The gas that is converted into stars during the merger is gas that would otherwise have formed stars later, more slowly, over a longer period. The merger accelerates the process. It burns through the remaining fuel in a concentrated burst rather than a drawn-out trickle. And when the burst is over, when the compressed gas has been used up or heated beyond the point of collapse, star formation in Milky will effectively cease. The merged galaxy will settle into its final shape, a massive elliptical, its stars aging on their individual timescales, its gas depleted, its central supermassive black hole, now a merged binary of the Milky Way's and Andromeda's original black holes, growing quiet as the last of the surrounding material is accreted or expelled. And then, isolation. The rest of the universe will already be gone, or rather, still there but unreachable, carried beyond the cosmological horizon by the accelerating expansion. Milky will be, for all observable purposes, alone. A single gravitationally bound structure, perhaps accompanied by the remnants of a few dozen dwarf galaxies from the former local group, adrift in an expanding void that contains nothing else it can see, nothing it can interact with, nothing it can reach. Avi Loeb, who has spent considerable time thinking about the long-term future of the local group, has described this as the last entry in the cosmic history book. After the merger, there are no more large-scale gravitational events, no more galaxy interactions, no more structural changes at the scale of millions of light years. The only remaining story is the internal one, stars aging, one by one, until the last of them burns out. There is something about this picture that carries a quality of dread distinct from the other timescales we have discussed. The death of the last red dwarf is trillions of years away. The evaporation of the last black hole is a googol of years away. Those numbers are so large that the mind floats over them without purchase, unable to feel their weight. But the Milky Way-Andromeda merger is close enough that the Sun will still exist when it begins, close enough that the event falls within the same order of magnitude as the remaining lifetime of the Earth's biosphere. It is not an abstraction, it is scheduled, and it is, in a sense, the last thing that will happen to us, the last large-scale event that will affect the galaxy we live in before the long silence begins. Loeb once pointed out that if Milky's inhabitants ever develop radio technology and begin broadcasting into the void, their signals will travel outward at the speed of light into an expanding universe that contains no one to receive them. The radio waves will propagate forever, growing fainter with distance and redshift, crossing the cosmological horizon of other hypothetical observers in other galaxy clusters who are themselves isolated and receding. The signals will never arrive, the messages will never be read, and Milky will sit in its expanding bubble of space, surrounded by a darkness that is not empty but is, for every practical purpose, unreachable. The last lit room in a building whose other rooms have been sealed off, one by hallways that stretch faster than anyone can walk. That image, the last lit room, is where the dread lives. Not in the death of stars or the evaporation of black holes, which are too distant to feel, but in the loneliness, in the knowledge that the merger, whenever it comes, is a door closing, the last guests arriving at a party that will never have another, and after the music stops and the gas is spent and the last blue supergiant goes supernova in one final theatrical flash, Milky will settle into the long quiet, with no company, no neighbors, no view, only its own aging stars and the memory encoded in the orbits of its outermost remnants that there was once something beyond the dark. There is a question that cosmologists have been trying not to think about for the better part of 2 decades, and it goes like this. In a universe that lasts forever, at a temperature that never quite reaches zero, is it possible for a conscious mind to appear out of nothing? The question sounds absurd, the kind of thought experiment that belongs in a philosophy seminar rather than a physics department. But it emerges directly from the intersection of thermodynamics, quantum mechanics, and the cosmological constant, and the physicists who have grappled with it include some of the most careful thinkers in the field. The reason it will not go away is that the mathematics, at least in its simplest form, gives an answer, and the answer is yes. The argument begins with a property of empty space that is easy to state and difficult to absorb. In a universe with a positive cosmological constant, which, as far as we can tell, is the universe we inhabit, the accelerating expansion produces a cosmological event horizon, a boundary beyond which light can never reach us, and just as a black hole's event horizon produces Hawking radiation, the cosmological horizon produces its own faint thermal glow known as Gibbons-Hawking radiation. The temperature of this radiation is extraordinarily low, roughly 10 to the minus 30th Kelvin for our universe, a number so close to absolute zero that it makes the cosmic microwave background look like a furnace. But it is not zero, and because it is not zero, the universe in its far future is not truly empty. It is a thermal bath, vanishingly cold, inconceivably sparse, but thermally active. Fluctuations happen, particles appear, and given enough time, those fluctuations can, purely by chance, assemble themselves into any configuration that is compatible with the laws of physics. This is where the thought experiment becomes genuinely disturbing. A thermal fluctuation that produces a single hydrogen atom is extremely improbable, but will certainly occur if you wait long enough. A fluctuation that produces a rock is far less probable, but still, given infinite time, inevitable. A fluctuation that produces a functioning human brain, complete with neurons, synaptic connections, blood supply, and a set of memories that feel coherent but correspond to no actual past, is so improbable that the number describing its likelihood would require more digits than there are particles in the observable universe. And yet, so improbable is not the same as impossible. In a universe that persists for an infinite duration at a non-zero temperature, every finitely probable event occurs. Not once, infinitely many times. These hypothetical objects were given a name in 2004 by physicists Andreas Albrecht and Lorenzo Sorbo, though the underlying idea traces back to Ludwig Boltzmann himself, who in 1896 proposed that the observable universe might be a statistical fluctuation in a much larger system at thermal equilibrium. Albrecht and Sorbo called them Boltzmann brains, and the name has stuck, partly because it is evocative, partly because the problem it describes has proven remarkably resistant to resolution. The problem is not that Boltzmann brains are possible, the problem is one of ratios. In the standard cosmological model, lambda CDM, the framework that fits all of our observational data with extraordinary precision, the universe approaches a de Sitter state in the far future, exponentially expanding, thermally active at the Gibbons-Hawking temperature, and eternal. In such a universe, the number of Boltzmann brains that will eventually fluctuate into existence is infinite. The number of normal observers, beings like us produced by stellar nucleosynthesis and biological evolution on planets orbiting stars, is finite, because the era of stars is finite. The ratio of Boltzmann brains to normal observers is therefore infinite to finite, which means that, under most reasonable ways of counting, a randomly selected conscious observer in this universe is overwhelmingly more likely to be a Boltzmann brain than a person. Sean Carroll, writing about this problem with characteristic clarity, described it as follows. A universe with a cosmological constant behaves like a box of gas at a fixed temperature that lasts forever. Given enough time, any arrangement of matter compatible with local physics will spontaneously appear. Atoms, viruses, people, and, more commonly, disembodied brains with false memories, floating briefly in the void before dissolving back into thermal noise. The overwhelming majority of observers in such a universe are not the products of cosmic evolution. They are momentary accidents of statistics, flickering into existence and out again, each one experiencing a single instant of confused consciousness before returning to equilibrium. If this sounds like the premise of a particularly bleak science fiction story, the physicists working on it would probably agree. Carroll himself has called Boltzmann brains cognitively unstable, meaning that the hypothesis cannot simultaneously be true and justifiably believed because a Boltzmann brain's memories and perceptions are, by construction, unreliable. If you are a Boltzmann brain, you have no reason to trust any of your observations, including the observations that led you to conclude that Boltzmann brains are possible. The argument devours itself. And yet the mathematical prediction remains, sitting uncomfortably inside the best fit cosmological model, and the community has not agreed on how to remove it. Some physicists argue that the problem is a signal, that the Boltzmann brain prediction indicates something is wrong with our cosmological model, or at least with our extrapolation of it to infinite timescales. Carroll has suggested that a better understanding of quantum mechanics, specifically of the vacuum state and its evolution in de Sitter space, might show that the far future of the universe is not a thermal bath at all, and that the conditions required for Boltzmann brain formation do not actually obtain. Others have proposed that our vacuum might be metastable, that the universe's current state is a false vacuum, and that it will eventually decay into a lower energy true vacuum through a process called vacuum decay, which would rewrite the laws of physics across the affected region at the speed of light and prevent the eternal de Sitter state from ever being reached. If vacuum decay occurs before the Boltzmann brain timescale, the problem goes away, but it goes away by being replaced with a different problem. One that is, in its own way, even more unsettling, and one we will come back to. The majority view among working cosmologists, as far as a consensus can be identified, is that the Boltzmann brain problem points to an incompleteness in our current theoretical framework rather than to a genuine feature of reality. The standard model of cosmology is an effective theory. It describes the universe within a certain domain of applicability, and extrapolating it to infinite timescales may simply exceed that domain, in the same way that Newtonian mechanics works perfectly well for everyday objects but breaks down at relativistic speeds. The Boltzmann brain prediction, on this view, is not a conclusion about the universe. It is a symptom, a sign that the model, pushed far enough, begins to generate predictions that are physically absurd and that a more complete theory would resolve. But the symptom persists, and it persists because the cosmological constant appears to be real, the acceleration appears to be ongoing, and no one has yet produced a theory of quantum gravity complete enough to say definitively what the far future of the universe looks like at the level of detail required to rule Boltzmann brains in or out. The question remains open, the discomfort remains unresolved, and there is something about the image itself, a conscious mind, assembled by chance from the thermal noise of an empty universe, existing for a single moment, perceiving a reality that never was, and then dissolving, that lingers in a way that the physics alone does not explain. It is a ghost story dressed in the language of thermodynamics, a single flicker of awareness in a void that has been dark for longer than any number can describe, experiencing something that feels like memory, something that feels like recognition, something that feels like being a person, and then gone. Not dead in the way that a person dies, with a history and a body and a world that continues after them. Gone in the way that a candle flame is gone when you pinch the wick, as if it had never been. Whether Boltzmann brains are real is a question for future physics to settle, but the fact that our best current model of the universe permits them, indeed predicts them in overwhelming numbers, says something about the kind of cosmos we inhabit. A universe where the laws of physics allow for the spontaneous, meaningless assembly of consciousness from nothing in the depths of an infinite dark is a universe that does not care about meaning in the way that we do. It is a universe that runs on mathematics, not on intention. And the mathematics, left to run long enough, produces everything, including minds that exist for no reason, remember things that never happened, and vanish without consequence into a silence that was already absolute before they arrived. That silence, the silence of the dark era, the silence after every structure has dissolved and every process has ceased, is not quite as absolute as it first appeared. There are ghosts in it, if the math is right, but the ghosts do not help. Freeman Dyson was not the kind of physicist who accepted defeat gracefully. He was the kind who looked at defeat, found a loophole in its logic, and published a paper about it. He had spent his career doing things that other people considered impossible, unifying quantum electrodynamics without a PhD, designing nuclear-powered spacecraft for the United States government, proposing that advanced civilizations might disassemble entire planets to build energy-harvesting shells around their stars. He was, by temperament and by record, an optimist of the most dangerous variety, one who could do the math. In 1979, Dyson published a paper in Reviews of Modern Physics titled Time Without End: Physics and Biology in an Open Universe. It was written, by his own admission, as a direct response to Steven Weinberg's famous remark in the first 3 minutes that, the more the universe seems comprehensible, the more it also seems pointless. Dyson disagreed. Not with the comprehensibility, he was a physicist after all, and comprehensibility was his stock in trade, but with the pointlessness. If the universe was open, if it would expand forever, if there was no big crunch waiting to collapse everything back into a singularity, then Dyson wanted to know whether intelligence could survive indefinitely within it. Not whether it would be easy, whether it was physically possible. His answer, worked out across 30 pages of closely reasoned argument, was yes, with conditions. The core of Dyson's proposal was a scaling hypothesis. As the universe cooled, an intelligent organism could slow its metabolism to match, think less often, think more slowly, hibernate for longer and longer periods, waking only when the ambient temperature had dropped enough for the next cycle of thought to be thermodynamically efficient. Each thought would cost less energy than the last because each thought would take place at a lower temperature, and lower temperatures mean less waste heat per computation. By carefully managing the ratio of thinking time to hibernation time, a sufficiently patient intelligence could stretch a finite store of energy across an infinite subjective experience. The total amount of energy consumed would converge to a finite sum. The total number of thoughts would be infinite. Life, in Dyson's formulation, could be eternal, not despite the cooling of the universe, but because of it. The proposal was elegant. It was also, in a way that is characteristic of Dyson's best work, deeply humane. The paper was not really about thermodynamics. It was about meaning. If consciousness could persist, if even one thinking entity could survive, in some attenuated form, through the long ages of cooling and emptying, then the universe was not pointless. The lights might go out, but someone would remember them. Someone would carry the knowledge of what had been, even as the evidence disappeared, even as the galaxies faded and the stars went dark. Dyson was not offering a practical survival plan. He was offering a proof of principle, a mathematical demonstration that the universe permits hope. For 20 years, the proof held. Then, in 1998, 2 teams of astronomers measuring the distances to Type 1a supernovae announced that the expansion of the universe is accelerating. The Supernova Cosmology Project and the High-Z Supernova Search Team, working independently, had reached the same conclusion. Distant supernovae were fainter than expected, which meant they were farther away than expected, which meant the expansion had been speeding up for the last 5 billion years or so. The source of this acceleration, dark energy, the cosmological constant, vacuum energy, whatever name you prefer for a phenomenon we still do not understand, changed the future of the universe in a way that cut directly through the foundation of Dyson's argument. Dyson's proposal required the universe to cool without limit. As the temperature approached zero, the cost of each successive thought would approach zero as well, allowing infinite computation from finite energy. But a universe with a positive cosmological constant does not cool without limit. The accelerating expansion produces a cosmological horizon, a sphere beyond which nothing can ever reach us, and that horizon radiates. The Gibbons-Hawking temperature, the minimum temperature of a de Sitter universe, is extraordinarily low, but it is not zero, and that tiny, irreducible flaw changes everything. If the universe never cools below a certain threshold, then the cost of computation never drops below a certain minimum, and the elegant convergence that Dyson relied upon, the infinite sum of infinitely cheap thoughts, fails. The sum diverges, the energy runs out. Life, in Dyson's formulation, is no longer eternal. It is long, extraordinarily long by any human measure, but it is finite. Lawrence Krauss and Glenn Starkman at Case Western Reserve University formalized this objection in a paper titled Life, the Universe and Nothing, published in 2000. Their argument attacked Dyson's proposal from two directions. The first was thermodynamic. In an accelerating universe, the Gibbons-Hawking temperature sets an inescapable lower bound on the cost of information processing, which means that any finite energy store will eventually be exhausted. The second was more practical, almost mundane in its simplicity. Hibernation requires an alarm clock, and alarm clocks consume energy. Even a perfect alarm clock, one that never malfunctions, never drifts, never fails to wake its owner at the appointed time, must use energy to operate, because the act of distinguishing now it is time to wake up from now it is not yet time is itself a computation, and computation requires energy. Krauss summarized this point in an interview with the directness of a man who had thought about it for a long time. Alarm clocks aren't reliable. Everyone who goes to work knows that. Dyson did not concede entirely. He and Krauss exchanged letters and arguments for months, and the disagreement crystallized around a question that neither of them could resolve with the physics available. Is consciousness fundamentally digital or analog? Krauss and Starkman treated information as discrete, zeros and ones, quantum states with definite values, subject to the minimum energy requirements of digital computation. Dyson thought in analog terms, continuous fields, dust grains communicating via electric and magnetic interactions, systems that might encode information in ways not subject to the same thermodynamic constraints as digital processors. In thinking about information and memory, Dyson wrote, "They think digital and I think analog." It was a genuine disagreement, rooted in genuinely unsettled questions about the nature of consciousness and the physics of computation. But the observational data, the accelerating expansion, the positive cosmological constant, had shifted the ground underneath the argument. Dyson's proposal needed a universe that cooled to zero. The universe, as far as we can measure, does not cooperate. Dyson acknowledged as much years later in a postscript that is more moving than most physicists would admit. He wrote that the time without end paper is obsolete because it assumed a linearly expanding universe, which the cosmologists believed to be correct in 1979. We now have strong evidence that the universe is accelerating, and this makes a big difference to the future of life and intelligence. He added that he preferred not to speculate further until the observational evidence became clearer. It was a graceful withdrawal, measured, honest, and entirely characteristic of a man who valued being right less than he valued being rigorous. But the loss that Dyson's retreat represents is not a loss of physics. It is a loss of something harder to define, something closer to a theological argument made in the language of thermodynamics. Dyson had offered the universe a way out. He had shown, or believed he had shown, that the cooling and emptying of the cosmos did not necessarily mean the end of consciousness, the end of meaning, the end of the capacity to ask questions and remember answers. The accelerating expansion closed that door, not with a dramatic slam, but with a slow, quiet pressure, the kind of force that does not announce itself, that operates on timescales of billions of years, that does not care whether you find its consequences acceptable. Dark energy does not negotiate. It does not pause for appeals. It simply pushes, and the universe gets colder and emptier and lonelier, and the finite store of energy that any civilization might possess becomes, on a long enough timeline, exactly what the second law of thermodynamics always said it would be: insufficient. Krauss, in an interview given around the time of his paper's publication, was asked what the discovery of dark energy meant for the long-term future of the universe. His answer had the kind of bluntness that tends to stick in the mind. A universe with dark energy is the worst of all possible universes for the long-term future of life. He was not exaggerating. And the reason his statement carries weight is that it does not depend on speculation about unknown physics or hypothetical technologies or future discoveries that might change the picture. It depends only on the cosmological constant being what it appears to be, a constant. If dark energy is truly constant, if the acceleration does not weaken or reverse, if the Gibbons-Hawking temperature is indeed the floor below which the universe never cools, then the future is exactly what the data suggests: long, dark, cold, and finite, not infinite. Finite, an unimaginably large but ultimately bounded amount of time during which anything interesting can happen, followed by an unbounded eternity during which nothing does. Dyson wanted to believe that the universe permits hope. The universe, as best we can measure it, permits hope for a very long time. And then it doesn't. So here is what we know. The universe is 13.8 billion years old. It has been producing stars at a declining rate for the last 10 billion years. The peak, cosmic noon, the era of maximum stellar production, occurred when the universe was roughly a quarter of its current age, and we have spent the time since then on the long downward slope of the Madau curve, watching the rate fall to a few percent of what it once was. The energy output of the nearby universe has dropped by half in just the last 2 billion years. The fuel, cold molecular hydrogen, the raw material from which all stars are made, is being consumed, expelled, and stretched beyond recovery by the accelerating expansion of space. No known process can reverse this trend. The curve goes down and it stays down, and at some point in the next few trillion years, it reaches zero. After that, the red dwarfs carry the light. They will burn for trillions of years, patient, dim, invisible to any eye not in orbit around one of them, and they will be the last nuclear furnaces in the cosmos. When the smallest of them finally exhausts its hydrogen, sometime around cosmological decade 14, the stelliferous era ends. The age of stars, the only age in which the universe has ever been lit, closes, and everything that follows is aftermath. The degenerate era, white dwarfs cooling toward black dwarfs that no one has ever seen because the universe is not old enough to have produced one, neutron stars fading, protons possibly decaying, each atom in every dead star coming apart over timescales of 10 to the 36th years, dissolving into positrons and gamma rays and a faint, meaningless warmth. If protons do not decay, then quantum tunneling takes over on timescales so vast that the numbers stop behaving like numbers and start behaving like abstractions. 10 to the 1500th years for matter to transmute, atom by atom, into iron. The black hole era, the last organized structures in the universe, evaporating through Hawking radiation over spans of 10 to the 67th to 10 to the 100th years. A solar mass black hole outlasting the stars by a factor so large that the entire stelliferous era is a rounding error in its lifespan. And the final moments of the last black hole, a burst of gamma radiation, a flash of heat in a cosmos that has been cold for longer than any number can convey, marking the last event the universe will ever contain. The dark era, infinite, featureless, without structure or gradient or change. A thermal bath at a temperature indistinguishable from zero, populated by photons and leptons so far apart that the concept of interaction loses its meaning. Time still passes in the sense that the parameter exists in the equations of physics, but nothing distinguishes one moment from the next. The clock runs. The clock has nothing to count. That is the trajectory. From fire to silence, from complexity to uniformity, from cosmic noon to the heat death of the universe. The second law of thermodynamics wrote this story before the first star ignited, and every observation we have made since, every galaxy survey, every supernova measurement, every painstaking census of stellar populations and gas reservoirs and energy output, has confirmed it. The universe is winding down. It has been winding down for most of its existence, and it will continue winding down, with increasing emptiness and increasing silence, until the winding is complete and there is nothing left to wind. It would be easy at this point to feel that the story is a cruel one, a universe that builds stars and planets and chemistry and consciousness and then, on a timescale so much longer than the era of building that the building seems almost accidental, takes it all apart and returns to blankness. A cosmos that permits life and then, without malice or intention, ensures that life cannot persist. The numbers are crushing. The timescales are beyond comprehension. The conclusion appears to be that everything we have ever known or made or loved is a temporary configuration of matter that will, given enough time, be indistinguishable from the background radiation of an empty universe. But there is another way to hear this, and it is, I think, the way it deserves to be heard, especially now, especially at this hour, especially if the sound of these facts has done what the best cosmic facts always do, which is to make the small things feel smaller and the large things feel unreachable and the present moment feel strangely, unexpectedly precious. Consider what it means to be here now, not in a philosophical sense, in a cosmological one. The universe has existed for 13.8 billion years. It will exist in some form for timescales that make that number vanish, and of all the eons that the cosmos will endure, the trillions of years of dimming starlight, the quadrillions of years of cooling remnants, the googol of years of black hole evaporation, the infinite featureless aftermath. We are in the one era during which the universe is lit, the one era during which stars burn and planets orbit and the sky from any vantage point contains something worth looking at. The one era during which the evidence of the universe's own history is still written across the sky in wavelengths that instruments can detect and minds can interpret. Krauss and Scherer showed us that this window is closing, that the expansion is carrying the evidence away, that future observers will inherit an impoverished sky. We are the generations for whom the sky is still full. This is not a consolation, it is a fact. And it is a fact that carries a strange emotional weight because it means that the awareness we have, the knowledge that the universe had a beginning, that it has a structure, that it is expanding, that it is dimming, is itself a product of cosmic timing. A civilization born 100 trillion years from now, orbiting a dying red dwarf in a galaxy that has forgotten its neighbors, would have no way to know any of this. They would look up and see a sparse scattering of faint red stars and, beyond them, nothing. They would build their physics from what they could observe, and their physics would be correct, and it would also be incomplete in ways they could never detect. We know what they will not because we are smarter or more advanced, but because we happen to exist in the brief window during which the universe is still willing to show its hand. And there is one more thing, the thing that sits at the center of all of this, the thing that the numbers and the timescales and the eras keep circling back to without ever quite stating directly. The universe does not know it is dying. It has no awareness of its own trajectory, no capacity to mourn its own decline, no mechanism for recognizing the difference between the fire of cosmic noon and the silence of the dark era. It is a system, vast, beautiful, governed by laws of extraordinary precision, but it is not a mind. It does not look back. It does not look forward. It does not know. We do. That is the strangest signal of all. In a universe that is winding down, that has been winding down for 10 billion years, that will continue winding down for timescales that dwarf comprehension, something has appeared that is capable of knowing this. Something assembled from star-forged carbon and oxygen, powered by a middle-aged yellow dwarf in the outer arm of an ordinary spiral galaxy, has looked at the data and understood the curve, has traced the trajectory from fire to silence and felt something, not despair, not hope, but something in between, something that has no clean name in any human language. Upon understanding that the light is temporary, we are the universe's way of knowing that it is ending, not its only way. There may be others elsewhere in other galaxies, under other stars, but one of its ways, and the knowledge itself, however brief and however small against the scale of what is coming, is not nothing. It is, in fact, the rarest thing the cosmos has produced, rarer than heavy elements, rarer than rocky planets in habitable zones, rarer than liquid water or organic chemistry or the first self-replicating molecule. The rarest thing in the universe is the thing that knows the universe exists. The stars will go out, the galaxies will fade, the black holes will evaporate, the atoms will come apart, And after a span of time so long that every number we have used in this story would be a vanishing fraction of it, the universe will reach thermal equilibrium and nothing will ever change again. This is what the physics says. This is what the data confirms. This is, as far as we can tell, how the story ends. But tonight, right now, this moment, wherever you are listening to this, the Milky Way is above you. 100 billion stars, most of them too faint to see, all of them burning. The photons reaching your eyes left their surfaces years or centuries or millennia ago, which means you are not seeing the sky as it is but as it was, a mosaic of the past, assembled by the speed of light into an image that exists only in the present, only for you, only now. The cosmic microwave background is streaming through this room at the speed of light, carrying the thermal fingerprint of the universe's origin, readable, for now, by instruments we have built and theories we have tested and minds that have spent a century learning how to listen. The evidence is still here, the window is still open. The universe has not yet finished erasing its own history. You are hearing this in the bright part, in the part where the lights are still on and the data is still legible and the sky is still deep enough to answer questions. It will not always be so, but it is so now, and now is not nothing. It is, in fact, everything we have.